it says you're from East Asia, and unfortunately your genome just doesn't work with metformin. You'll have to take this inferior generic medication.
Oh no, if only there was a way to make this great drug metformin work for my Asian genome too.
Scientists can help.
Practically everyone knows of type 2 diabetes. It's a form of diabetes that's primarily characterized by insulin resistance. That is, the body's hepatic cells are unable to open all of its membrane receptors and allow glucose to be let in and made into ATP. This thus causes a buildup of glucose within the bloodstream, otherwise known as hyperglycemia. While there's no cure for type 2 diabetes, metformin is a highly popular drug that is used to treat individuals with this disease. Specifically, metformin decreases gluconeogenesis, or the liver's production of glucose, and it does this by increasing cell receptor efficiency and allowing for more glucose to be let in. Metformin enters cells via organic cation transporter 1, and in doing so, it decreases mitochondrial cellular respiration, which in turn lowers blood glucose levels.
So why are we talking about metformin? What makes metformin so special? Well, for one, metformin acts like any other diabetic medication in that it decreases lactate to glucose conversion and decreases hepatic glucose output. However, what makes metformin so unique is that it also directly increases the body's sensitivity to insulin. Now, what this means is that when metformin works, the patient oftentimes only has to take metformin as their one diabetic medication, as opposed to when metformin doesn't work, they also take a cocktail of medications to get that same diabetic treatment, increasing prescription complexity and increasing patient cost. Another thing that metformin does really well is that it facilitates weight loss, and this is thought to have happened because it increases the oxidation of lactate and increases the uptake of glucose in adipose tissue, which is then burned through use. In short, metformin decreases blood sugar levels while, without increasing weight gain and without the required increased insulin plasma concentration levels that other medications need.
So what is the organic cation transporter 1? Well, OCT1 provides the first step in detoxifying compounds, namely drugs. As you can see in the top right-hand corner of the diagram, OCT1 assists in transporting compounds from drugs that have just entered the liver. Thus, it contributes to how patients respond to the drugs that are supposed to be treating them. However, OCT1 does not transport indiscriminately. Think of it like a door in the membrane. Some people have doors that let other people like metformin through, while other people have doors that do not. Unfortunately, the variances in certain groups of people reduces the ability to effectively use and distribute metformin as a medication for diabetes.
Now, understanding how OCT1 and metformin interact allows us to understand why people with ineffective OCT1 alleles do not see the therapeutic benefits of metformin. It was found that the deletion of OCT1 led to the reduction of AMPK phosphorylation. The result of this was that there was no reduction in gluconeogenesis, which is the whole goal of metformin when treating type 2 diabetes. Because OCT1 does not let metformin into the hepatic cells, there is less access to the target tissues, which thus results in a greater amount of metformin in the bloodstream. Because also the liver cannot process and eliminate metformin, metformin exists in a longer time in the body.
OCT1, just like other proteins within the body, is subject to differing polymorphisms. The regions in the gene that encode for OCT1 can differ from individual to individual, and as a result can alter the affinity and function of the overall protein. In normal metabolic function, the varying alleles are not typically expressed, as OCT1 can behave normally in endogenous transport. However, it is only in the use of medication that polyspecifically interacts with OCT1 where OCT1 variance becomes extremely apparent, such as in metformin. Different regions of the world have different frequencies of these alleles, and as such, metformin may be more or less effective depending on where you live and depending on your ethnic background.
So why is this important? Essentially, there are genes that encode for proteins involved in detoxifying drugs. Now, when there are variances in these genes, then there's great variability in the response to the drugs, so the drugs don't work like they're supposed to. Now, this medication, metformin, is used to treat diabetes, but now such a large portion of the population can't use it. There is such little research involving OCT1 uptake, so how do we know that there's a relationship? Well, people have studied how metformin is distributed in the liver with mice. Essentially, with OCT1 knockouts, metformin was not distributed as well as with the wild-type mice. So researchers knew that there was a detected difference, they just didn't know why. Now, our original research will work towards determining the frequencies of such variants, and we hope to apply this information to modify metformin in the long run and create a more effective treatment for diabetes for such populations.
So our objective is to conduct further research on the genomes of individuals, specifically in Western China and Mongolia, that are known to have these OCT1 forms that don't allow for metformin efficacy. We propose running genetic tests on these individuals in order to see if there's any significant difference between their forms of OCT1 and the OCT1 seen in normal individuals. In understanding these underpinnings of these variations, we'll be able to eventually enhance current type 2 diabetes medications such as metformin, and in the long run, this research will act as a foundation for further research that can help engineer even more effective type 2 diabetes medications. Because OCT1 forms vary from individual to individual, collecting and analyzing this data from Asian populations will allow us to make type 2 diabetes medications more tailored to the individual.
So that brings us to our methods. What we want to do first and foremost is survey the genome of the region. It's much too costly for us to do this on our own. So what we plan to do is collaborate with local hospitals in the central areas of the continent, paying special attention to urban centers like Ulaanbaatar. Through this cooperation, said hospitals can screen their patients and conduct simple genetic tests, relaying and sending that information back to us. This way, the cost of surveying such a vast region is cut significantly, with the most specialized portions of the study being data computation being conducted in a more centralized manner. This leaves the issue of collection the only other remaining significant cost, which can be conducted by workers within these hospitals without significant training or specialization. We've analyzed various methods and found this to be the most effective in finding the data we are looking for.
So from this project, we expect to see significant mutations in East Asian population in the OCT1 sequence of the genome. Of these populations, we would expect to find variations in mutation frequency and genomic location by geographic region, with which we would compile a data set of regional general similarities of OCT1 mutations. We would analyze these mutations and quantify which populations exceed the threshold for metformin ineffectiveness. Understanding this threshold and which populations and regions correspond to which mutations will allow us to identify the genomic location of areas of high OCT1 mutation density by geographic region. In short, this would allow us to map geographic regions to certain specific OCT1 mutations. This was what we mean by more personalized treatment, in that the information gained in this study would allow development of mutation-specific medication that would be far more personalized than it is currently.
So we have identified a few possible problems with our study. The first being a cultural barrier, since we are going to a foreign country. However, we have designed our method to specifically eliminate this cultural barrier, since the patients will be interacting with their local hospitals and their local doctors. Therefore, we won't have to overcome this language and cultural barrier. Another problem is that hospitals in Asia are not spread evenly. From this map, the density of hospitals is higher density in urban locations. As a result, a greater proportion of our data would be from urban locations rather than rural. However, since urbanization has been such a recent phenomenon in Asia, the difference in the OCT1 alleles between rural and urban populations will be extremely minimal and thus won't affect our results extensively. By overcoming these problems, we will be able to effectively collect the needed information about OCT1 allele frequencies in Asia, which will thus set the foundation for the creation of metformin-like medication in the future that will be effective for people with different OCT1 variances.
Here, Gloria, another dose of your generic inferior diabetic.
Wait!
This is a new version of metformin that works for people of Central Asian descent, all thanks to the grant we received funding for.
Yay!